Today we're going to look at continuity. Continuity is something you probably talked about. You may have talked about in Algebra 2. Hopefully you talked about it in pre-cal at least a little bit. The simple sort of, I call it the baby explanation for continuity, is if you can graph the function without picking up your pencil, then it's a continuous function. But that's hardly a definition, right? That's more of a description. So we'll start with the idea of continuity at a particular point. A function y equals f of x is continuous at an interior point C of its domain if the limit as x goes to c of f of x is equal to f of c. So where the function is headed is equal to what the value of the function is at c. Okay, notice that in this it says at an interior point C of its domain. So that means the function has to be defined at C. So the function has to be defined at C, the limit has to exist, and they have to be the same. Some books present that as three different things, but if this is true, then both of these have to exist. You know, does not exist doesn't equal does not exist, because does not exist is not a number, right? Only numbers are equal to each other. We can also do continuity at endpoints. The College Board avoids these for the most part. Your book doesn't, and you know, whatever school you go to, you know, may go, yeah, we do continuity at endpoints and stuff. So we present it here. A function y equals f of x is continuous at a left endpoint A, or is continuous at a right endpoint B of its domain if the limit as x approaches A from the right of f of x is equal to f of A, or the limit as x approaches B from the left of f of x is equal to f of B. One of the interesting things about that sometimes confuses people is at a left endpoint, well, we can only approach from the right. That makes sense? If we're coming up to the left endpoint, the only place we can come from is the right. So let's discuss the continuity of y equals f of x at x equals 0, x equals 1, x equals 2, x equals 3, and x equals 4. All right, so I always start with the function. So it'd be nice if I turned on my pen. So what is f of 0 equal to? 2. And since this is the left endpoint of my visible domain at least, and the limit as x approaches 0 from the right of f of x is also equal to 2, then f is continuous at the left endpoint x equals 0. All right, let's move on to 1. What is f of 1? 2. But what is the limit as x approaches 1 of f of x? Pardon? I just didn't hear you.
Wait,
what?
No, I don't.
Say what you said.
Is it 2?
Nope.
Does it not exist?
Yeah, it does not exist. Therefore, f is not continuous. at x equals 1. All right, let's go on to 2. What is f of 2? 1. But that's not equal to the limit as x approaches 2 of f of x, which is equal to what? 2. As x approaches 2, what value does the function get close to?
Oh, okay. Wait, so why isn't that for, wait.
As we approach 1, one side approaches 1, but the other side approaches 2.
Okay.
They go to different places. Therefore, f is not continuous at x equals 2. All right. Let's move on to 3. What is f of 3? 1. And what is the limit as x approaches 3 of f of x?
1.
Also 1. So being hyper lazy, I just write it like this and then stick an equal sign in here. Therefore, f is continuous at x equals 3. And then at 4, f of 4 does not exist. Game over, man. Therefore, f is not continuous at the right endpoint x is equal to 4. And that's, kind of all the different possibilities. So a function is continuous on an interval if and only if it is continuous at every point of the interval. That makes sense. It has to be continuous with every one of those points. A continuous function is one that is continuous at every point of its domain. Now, this is where students get into trouble. So let's look at y equals 1 over x. Hopefully that's one of those ones where you know exactly what that graph looks like really quickly. It looks sort of like this. Is it a continuous function?
No,
Why not?
because it's not defined at 0.
Okay, so is x equals 0 part of the domain of this function?
Oh, it's not.
No. So by this definition, and I don't like this definition, it still bugs me to today, this function is continuous because it's continuous everywhere that it's defined. Now, personally, I like to say it's continuous on its domain instead of just saying it's a continuous function. I would say that y equals 1 over x is continuous on its domain. And that's true, and everybody agrees with that. When you show somebody this and say, is this a continuous function? The answer is yes, by this definition. Okay, and again, College Board rather wisely kind of doesn't ask a lot of questions about things like that. So the answer to this is yes. It is continuous at every point in its domain. All right. Jake, you look like you're thinking. No?
Just taking it in.
Just taking it in? Okay. All right. So some properties of continuous functions. If the functions f and g are continuous at x equals c, the following combinations are also continuous at x equals c. So if you add two continuous functions together, or two functions that are continuous at a point, the sum will be continuous at that point. The difference will be continuous at that point. The products will be continuous. If you multiply by any constant, the new function is still continuous. Now, quotients you have to be careful about. The quotient will work provided that g of c is not equal to 0. Because then you have 0 in the denominator, and this function does not exist at that point. So it can't be continuous. And then composites, g of f of c, this works provided that g is continuous at x equals c. Excuse me, g is continuous at f of c, whatever that turns out to be. So an awful lot of functions that you know are continuous functions. Polynomial functions. Rational functions, by the definition, are continuous. You're like, well, what about removable discontinuities and vertical asymptotes? Well, the function's not defined there. So we don't care about those. Trig functions, those are all continuous functions. Or again, as I would prefer to say, they're all continuous on their domain. I think that's a fairer way to say it. As are root functions and absolute value functions. Now, this last part that we're doing today, super important idea. And it's one that you already intuitively understand. Let me give you an example. So, this morning when I left my house, it was 78 degrees, 97% humidity. Okay? Today when I get home, it's likely to be 98 degrees or so. At some point at my house today, is it going to be 85 degrees? Yeah, it has to be. Okay? So, as I'm driving to work, the gas price at the HEB, I think it was $2.88 a gallon. Let's say that on my way home today, it's $2.95. Does it have to be $2.90 at some point during the day? No. Why are these two situations different? What is it about temperature that is different than the price of a gallon of gasoline?
Like the sun is like always changing with the light.
Wait a minute, the sun, what?
Like the sun is like always like rising and setting like at like every second.
Right, but I'm talking about temperature.
Well, the temperature is like always rising like every second, like as the sun is out. But then like gas, like they can just change it at like any point.
Okay, So what kind of a function then is temperature as opposed to the price of a gallon of gasoline? I'll give you the hint. It's the title of today's lesson.
Temperature is continuous?
Temperature is continuous, but the price of a gallon of gasoline is not. Because the temperature is continuous, if I have, two different temperatures at a location, I know that the temperature has to go through everything in between those two, right? Whereas with the price of a gallon of gas, I do not know that. I think there's some fruit flies in here too. I just have a whole menagerie of flying things up here. So, here is the intermediate value theorem. Frequently it gets abbreviated IVT. This is one of 3 existence theorems that we do. This guarantees that something exists. It doesn't tell you how to find it or where, what's going to happen, but it says something's going to exist. So, a function y equals f of x that is continuous on the closed interval from a to b takes on every value between f of a and f of b. In other words, if y sub 0 is between f of a and f of b, then there exists at least one value, x equals c, such that f of c is equal to y sub 0. So in this case, there's only one, and it's here, where f of c is equal to y sub 0. Now, is it possible that it could happen more than once? Yeah, like if you do the temperature example, let's say that late this afternoon before I get home, a thunderstorm comes through, drops the temperature 15 degrees, and then it comes, as it frequently does here, comes right back up to where it was. Well, there would be 3 different times where the temperature was 90 degrees or 85 or whatever it is that I said. Okay? But this theorem guarantees that at least once you're going to get all those intermediate temperatures, or in the case of a function, all those intermediate values. Okay? Any questions about that? Okay, then that's it for today's lesson.